Hello everyone, this is Jeff Wilkerson, Professor of Physics at Luther College. We have a series of videos of how we go about using KaleidaGraph in various ways, and this is the next in that series. What we're going to do today is we're going to look at a double Gaussian, and we're going to try to make some decisions about whether we like two Gaussians fit to a data set or a single Gaussian. We're not going to do this in a terribly technical way, so we might do a little bit of that in a future shoot. But for the filming that we're doing here today, we're just going to get an idea of how to process the data a little bit. Save the statistical decision making for later on. So let's go right away. Let's go ahead and grab KaleidaGraph and see what we can get here. I'm going to share my KaleidaGraph window with you. Hopefully you can see that there now. So we have a column of data. You can see the data that's in there. That's data that I pasted in. I don't think it's real data. I think I made it up, but I don't really remember the history of it. I used this in a course assignment recently where I asked students to do some of the work we're going to be doing here today, to be thinking about how we want to approach this data set. And in that assignment, I said, let's assume these were color indices of stars. And we're asking the question, do we have any evidence that there are two populations of stars there with two different mean color indices, but spread around those color indices? So the first thing we're going to have to do is we're going to make a histogram of this. So let's go up under here and bend the data like we like to do. We make a step plot. You can play around, and I encourage you to do this with the number of bends and see how it changes the feel of the data set that you have right there. So definitely try it with more bends and fewer bends and see what the quality of the fit is and what you think about that, and see how it affects the quality of the fit. If you've overbend the data, then it's going to be noisy and it's going to be hard to fit. If you've underbend the data, you're going to lose features like we might be looking for right here, dips between two possible peaks that might be real or might be noise. We don't know. It might be Poisson statistics is probably a better way to think of that than noise. But anyway, we're not sure about that. And so in any event, you don't even have a chance to look for that if you underbend the data. And if you underbend it too much, the quality of your fit, you don't have enough free parameters for your fit to work. But so we got that calculated. Let's copy it to the clipboard. And just for the heck of it, to keep things clean, let's paste that into a new window. And as you know, if you've watched any of the videos that I've done before, we like to, when we do a graph here, we'll do a scatter plot. Typically, if we're looking at paired data sets and trying to see, so we don't imply to the world that we're doing some kind of curve fit, or we don't imply to the world that we know what's going on between any two data points that we took. So generally best to use a scatter plot. But for a histogram, we connect the dots because this isn't raw data. This is processed data, and we expect this to look like a step plot. And I was talking to you too much and didn't actually see what I just did there. So we're going to go up and do this again. And we're going to do a line plot, and we're going to go here and here, and I should hit plot instead of cancel, I guess is probably what I did. So there we go. We've got this. I've played around with this a little bit. Apparently, I didn't change the color of my y-axis. I want everything to be black for the grids and the ticks. We got rid of all of the grids, but the axis we want to be black there as well. Okay. While I was there, I should have get this thing started at 0. Histogram looks funny. If you've got negative axis, you don't have it sitting right on the horizontal axis. There we go. I like that. So basically the question we're asking here is we're going to try to fit one Gaussian to this data set, and we're going to try to fit two Gaussians to this data set and to see what the difference is. Basically, we're not going to do a whole lot with quality of fit, but we'll play with that. We can look at some residuals if you'd like and do that sort of thing. So let's start by let's clean this up a little bit just so I hate nonsensical axis labels. So let's make that number of counts, number of stars. So we'll just keep this myth going that this is stellar color indices. So we're going to put the number of stars up there, and this is our color index. And if we want a title for the thing, we can say color index is distribution. All made up. It's all fabricated, but that's okay. So we're telling a fictional story here. Get rid of that. Now that looks like a real plot to me. I like the way that looks. So we can go forward with this. Let's try to fit a single Gaussian to it, shall we? So let's go in here and look at this and say we're going to come up here and we are going to do a curve fit, general, and Gaussian, and we're going to define it. And what I'm going to do this time is, if you've watched any of the other videos where I fit Gaussians, we have this M1 out front. That's a variable that floats the Gaussian up on a background. And that's a great thing to have. You know, for instance, if we're fitting spectral lines, if we have an emission line on a continuous spectrum, we need to subtract out that continuous spectrum. So we need to float this up on top of that continuous spectrum. And that's what M1 is there for. More often than not, what we end up using M1 for is to cheat. And that is to say, if we use that M1, we might say that this background back here is 1 or 1.5, and we're floating this entire histogram up on that background that isn't really a background at all. It artificially narrows our peaks. So rather than artificially narrowing our peaks that way, we can take the M1 out. I just want to show you this. If you have a fit that's defined like this, you can take out a variable. Just bam, it's gone. And then come over here to give it its starting value. You don't want to give a starting value to something that doesn't exist, so we take it out there too. So we just took M1 out of the fit. M2 is the overall scale height up here. For our single Gaussian, I'm going to call it, I don't know, let's call it 12. M3 is the mean of the Gaussian in here. Let's call it 0.77. M4 is the standard deviation. Maybe 0.03 is good enough to get this job done. Let's see if this worked. Yeah, okay. That seems like a reasonable fit. You see the Gaussian goes to 0 down here. So we got rid of that background it was floating on. That's probably fair for this. Let's go up here under object, under plot, excuse me, and say display equation. And we get the fit parameters that are up there. And I'm just going to write those down. It said the mean of this fit was 0.76. 0.765, let's call it. 0.7646 was the mean. And the standard deviation was 0.037, what is it, 8, 0.0378. So that's the M3 and M4 that we have right there, the mean and standard deviation. So that's all groovy. It's all great. We have another video out there where we talked about finding residuals, but let's go up here and let's find the residuals, how much these points missed by. And so what I'm going to do up here is I'm going to go to curve fit again, and I'm going to go to general, and I'm going to go to Gaussian, and I'm going to ask it to copy residuals to data window and see what it does. Did something. I saw the data window jump back there, right? So the residuals tell us how much we missed at each of these points. Okay, so it says, it's a little bit funny in a Gaussian because we've doubled up the points in a step plot like this, but that's okay. We're not going to worry about that too much here. We're going to look at that. We're going to say, now, if I just found the mean of those residuals, let's do that. Let's say function statistics and find the mean, and it says the mean's 0.057. Okay, so it said on average we missed, predicted we missed by 0.05. But that's because sometimes we missed high, and sometimes we missed low, and we missed quite a bit high, and we missed quite a bit low. And that's our first hint that maybe this is better fit with 2 Gaussians instead of a single Gaussian, that there's a peak here and a peak here. And so what I want to do is I'm going to come up to these residuals, and I'm going to square those residuals. I'm going to say, let's just for the heck of it, write it in a different column here. And let's say that C3 is equal to C2 squared. So we squared those residuals out. And now I'm going to take the mean of that. Okay, so I want to find the mean of the squares. So I'm going to come back up here and I'm going to say statistics. It looks like the mean of the squares is 3.042. 7. So I'm going to just say, okay, that's good. We've got the mean of there being 3.0427. So we've squared it. Everything's positive. It turned all of those deviations into all those residuals into a positive number. And rather than just plot it on the computer, I'm going to do it on a calculator. It's going to be 1.7, right? I'm going to take the root of the mean of the squares. I'm going to take the square root of 3.0427 is what I recall. It doesn't really matter. 1.74. So we ended up with 1.74 is the root of the mean of the square deviation, the RMS deviation. The root mean square deviation is that 1.74. Okay, that tells us, that gives us a sense of how much we missed by. That shows up this chi-squared of 133, 134 over here. But let's look at how this sausage is made. Let's look at how we're getting into this, how we're getting into some of this of what we're doing here. So this is all good. Great. I like what we did. Actually, let's just write it on here. Let's do this. Let's come up here. We're doing all kinds of stuff that we've done here before. So let's click on the plot and let's write on here to say, we make a box and we say RMS deviation of fit is what I'm going to call it. Because what is the RMS deviation? It's what we just calculated of the fit from the data, or the data from the fit is 1.74. So that tells us we got a little characterization of the goodness of fit right there. Okay, all good, all good. Stop that. I'm pulling my plot apart here. I don't want to do that, but that's okay. Okay, so this is what we got going on here. I dragged that plot down a little bit low, but we got this RMS deviation fit 1.74. Let's go through this whole thing again, and I'm just going to rebin it. Function, bin data. I made 21 bins. I'm going to copy it to the clipboard just like we did before. Say OK. I'm going to open yet another new window. This is how I get 400 windows open. I do this all the time. I'm going to paste the data in, and I'm going to make a step plot again. So I'm just starting all over from scratch, so I don't write anything over what I already did. I don't get two data sets mixed up or anything like this. And we're going to try to fit it with two Gaussians. Oh, this is getting fun, right? So let's come up here, gallery, and do linear line, just like everything we just did before. It should remember what we did before. So yeah, we don't have to change any colors or anything. But I always want that to be 0, because it looks weird to me to have a histogram floating on nothing, floating on air out there. We call that color index. We don't need to go through all this again. I just can't help myself, because axis labels that are meaningless they bother me when I see them. Number of stars like that. So we're all good right there. So this is we call that a color index histogram, I think. We're just recreating the graph that we made, the histogram graph that we made a minute ago. There you go. Beautiful. We got it again. Everything's great. Everything's coming up statistics. Okay, so let's come in and let's do a curve fit that is a double Gaussian this time. So let's come up here and do a general Gaussian, but we define it. And what we're going to do is we're going to get rid of M1 again. We got rid of M1 last time. Let's get rid of M1. There it is. Everything looks good again. But now what I'm going to do is I'm going to put a plus sign in there. Make sure I'm where I want to be. I'm on the... Did that make the space where I want it to be? It did. Okay. So I'm going to do a plus sign there. And I'm just going to take this Gaussian that we have right here and just rewrite the whole thing. Do a Control-C and a Control-V. And I have two different Gaussians added together. But now I can't have them be the same variables, right? So if that's M2, M3, and M4, let's make that M5. We could go back and use M1 again, but let's not. M6 and M7. So now M6, M4, M5, M6, and M7 are the parameters of the fits for our second Gaussian that we're adding to the first one. So we defined this thing last time. We said M2 was 12. We'll just keep that there. That seemed to work. M3 we said was 0.77, but now it's just going to be this upper peak. So maybe it's a little bit shifted up. So let's call it 0.78. And it's probably going to be quite a bit narrower. So instead of the point, I don't forget what the fit parameter, we had 0.04. Let's call it 0.02 here. All right, but now we got to give it guess values for these other things too. M5 is going to be that smaller peak down here. So let's give M5 a starting value of 8. I don't know, I'm guessing. M6 is, let's give it a starting value. That's our mean of this Gaussian peak right here. So let's call it 0.74. Don't know if that's good enough or not. It might be a little above that. And let's call the M7 0.02 as well. That's the standard deviation of the smaller peak. Okay. We could have forced these it's possible I could have said, okay, let's actually force the standard deviation of this peak to be the same as this peak. Then I would have just rewritten this. Instead of calling this M7 as the new standard deviation, I would have called it M4 still, and we wouldn't have had to define that. But let's see how that worked. Whoa. Look at that. So it didn't do a fabulous job of coming down and grabbing that. Okay, it didn't come down and grab that low point as well as we might. But what we can do is a future, we can talk. One way to think about this is to say there is numerical scatter in these data points. And that numerical scatter we can often think about as just being a Poisson distribution. And it's going to, so you can think about, well, how many standard deviations is that point below the fit right there? But in any event, we can ask, is this a better fit than what we had before? And we have all of these parameters out there. So now we say we have one peak at 0.774, and the other peak is at the mean of 0.738. And one of them has a standard deviation of 0.022, and the other one has a standard deviation of 0.014. So, for example, this is the means and the standard deviations of those two peaks. This is a beautiful thing to see. We could try floating it on this background. I say, well, maybe this is noise out here, right? Maybe we do want to float that up, and maybe we'd get a better fit. But just because we get a better fit doesn't mean that's reality. We want to be careful about that a little bit. But let's calculate the residuals like we did last time, and then we're going to be done. We're going to compare those residuals to what we had last time. So we're going to come up here, and we're going to go to curve fit again, and we're going to go to general, and we're going to go to Gaussian, and I'm going to say copy residuals to the data window. There's our residuals to the data window. Okay. And now we come over here to the data window, and we're going to do our Control F to pop this up. And we're going to say, let's make sure those are right. Always make sure that I knew they were right, but let me make sure the data column numbers are what we're calculating with. We're going to run it. There's the squares of our residuals. We're going to find the mean of those. So we're going to come up here and do statistics. The mean is 3.64. That's very interesting. That's bigger than what it was with the single Gaussian. Okay, so the double Gaussian doesn't seem to have done a better job of fitting, because the mean of the square of the residuals is this 3.64. And you can see it's because some of these miss by a lot down in here. So we have some of these, it's probably, it's not that point, is it? It's over here. You got a point that missed by a heck of a lot. And so you've got some of these values that really don't look like they did a great job of fitting. And it could be what we talked about last time. In fact, that you've got this step across here, and this isn't really necessarily the best way to go about doing this data analysis, is finding the residuals. I was just trying to find an example so you could show a mechanical example to figure out how to do this in KaleidaGraph, but probably we don't necessarily want to ask this curve fit to fit both ends of these data points out in here, right? We probably just want to fit to the middle right here, like there and there. Anyway, that you see what's going on. But we said, okay, the square root of 3.6 is going to be, basically 1.8. Is 1.9. So basically, our RMS deviations, the way we calculated them this way for these two fits, are about the same. And you can take a look at this and you can get a sense of why they're about the same. So what this is a reminder to us, there's a couple of interesting things going on here. One of the things is, what this is a reminder to us is that this should be a couple of interesting things. I don't know what I did, but I obviously didn't bend the data the same. This data is more finely bent than this data. And so I didn't do a good job of creating the same bins. I wasn't paying enough attention when we went through there. And so that's one thing that might be going on, is we might have underbend this data a little bit, or overbend this data a little bit. But it's also possible that it just wasn't, this one bin being low is very, very, very hard to make an argument that you have a bimodal distribution, that you have two peaks, when you just have a single bin that's low between these two. And so this one might have done a different job over here, because if there were two or three that were below the fit in this case. I'm actually curious what I did there, because I wasn't paying enough attention to what was going on. So I'm going to go back to the data window and do this again. Basically, we're done here. You've seen how we made a double Gaussian, and you've seen how we made a single Gaussian. But I want to go back and find that data window, just because it's fun, and I want to do this bin data. And I thought what we did was 21 bins, but I wonder if I didn't recalculate it. I get busy talking to you, and I stop doing the stuff that I'm paying enough attention to what I'm doing as I go along. And let's see if this looks more like, that looks more like the plot we were expecting to see, the single Gaussian plot. Yeah, this one is more. So I changed the bending on us, which means it wasn't a fair test between the double Gaussian and the single Gaussian. Okay, so let's just go back really quickly and try to apply that Gaussian. Since we didn't change anything, we shouldn't have to redefine anything. So we'll come up here under Gaussian. It should still have the two Gaussians defined for me, and it doesn't. Okay, so that'll kill a little bit of time here as we're moving along. So we're going to double this thing up again. We're going to come in here and say plus, and copy. Copy that and paste it over just like we did before. You're watching the exact same thing again. How riveting that must be for you. So let's actually do it differently this time, like we talked about last time we went through. So we're going to keep the M4. We're going to force the two to have the same standard deviation. I don't know, I'm not sure what that is, but we're going to say you're going to have the same standard deviation, and you can have different scale heights. So let's make that M5 still. And let's make the mean be M6. But we're going to keep that as M4 to force the two different distributions to have the same. We may have some theoretical reason. Again, I made this data up, so I don't have any great theoretical expectations for it. But we might have some theoretical reason to believe that they should have the same widths. The two peaks should have the same widths in there. So let's force these to have the same widths, and let's call that width 0.02. And this M1 we said was 12, I think, last time through, and M2 is 0.7. Let's just see what that fit. Oh, I can't. M4 M3 was 0.7. Goodness, I didn't get rid of that M1 like I was supposed to. We're off script now. M2 is 12. M3 is 0.775. M4 is 0.02. That's the standard deviations of the two different peaks. M6 is going to be this lower peak that was down in here. Last time it fit to 0.737. So let's call it 0.735. And no, that's the scale height. Yeah, M6, I forgot the scale height. So let's go to the scale height as M5 is equal to 8. Okay. Okay, so maybe it did a little bit better fitting this time through to fit that peak down through there. So here we forced these to be. Let's compare those two fits to see what you see. It still has trouble. It's still possible that's just noisy low, right? It still has trouble fitting that. Let's come up here and let's calculate the residuals. General Gaussian copy residuals. There it is. Okay, come over here, do our Control F. Let's run this thing. And you see we don't have any of those big numbers that we had before. So it seems like it did a little bit better a fit job. And to say function statistics, and it's 1.91. So this is now, that was 3 before, with the first time through. And so the square root of 1.9144 is, I'm going to come in here and I'm going to say root 1.9144 is 1.38. So now I'm going to come over here and I'm going to say this is what we had here before. Control C, and I'm just going to copy it over here. Control V, and I'm going to say that's 1.38. So the RMS deviation of the fit from the data is 1.38 when we did a double Gaussian, and it's 1.74 when we did a single Gaussian. That's comparing that number to that number you see. So that implies a little bit better fit from the double Gaussian. But you saw that it was a worse fit when we underbend it. So this is very sensitive to bending, and you have to be very careful as you go about this. And it's not clear at all. We would have to do a lot more statistical work that we're not going to do here today. I've already taken enough of your time, but we'd have to do a lot more statistical work to try to make a claim whether that was a statistically meaningful difference between these two fits. You see the goodness of fit parameter 0.89, R value 0.81, chi-squared's 84 over here, 133. Everything suggests this is a slightly better fit. Whether it's a meaningfully better fit, and we could say, yeah, we have evidence that there are two color index distributions. We're going to have to be a lot more careful about what we're doing here. And we can do that in a future video. But for what we wanted to get done here today, where we just wanted to practice making a double Gaussian fit and practice our residual work again, and practice some of this single Gaussian, double Gaussian residual kind of thing, making histograms. This was good practice for us. So I hope you found this video helpful, and I hope you found it enjoyable. And I think that's good. That's what we have for you here today, and we'll have something new for you in the future. Take care, everybody.